This is the video for Chapter 14. We'll be talking about linear correlation and regression. So first we're going to talk about the linear correlation coefficient, R. And this is just a measure of how strong the relationship is between two different variables, representing quantitative data. And in order to find R, although your textbook has lots of formulas to find R and the regression equation, we're definitely going to use technology for this. You can use your calculator, and in this video I'm going to show you how to use StatCrunch for this. And keep in mind that we're only talking about linear relationships. So when we graph paired data, we want the points to approximate a straight line pattern. We say that a correlation exists between two variables when the values of one are somehow associated or related to the values of the other. And again, the linear correlation coefficient, R, tells us the strength of that linear relationship. We can see this relationship by creating a scatter plot. Here's some examples of scatter plots and the correlation coefficients that correspond to them. In this one, we would say we have a positive correlation because the general pattern of the data is going up as we go from left to right. If we entered all this data and found the correlation coefficient, it would be 0.851. Now in this graph, the trend of the data is going down from left to right, so this would have a negative correlation. And notice that this one is a little bit more close to a straight line pattern than this one was. The points in this one are more spread out. The points in this one are at least closer together and look a little bit more like a straight line pattern. The value of R, in this case, it's negative because we have a negative correlation, but it's closer to -1 than this one was to 1. And in this graph, our data points are just all over the place. There's no linear relationship that we can see at all. So in this one, we'd say there's no correlation, and if we actually calculated the value of R, it would come out to be 0 or very close to 0. Here's another set of points that have been plotted, and notice that you can see there's a relationship here, but it's not a linear relationship. In other words, it's not a straight line. In this one, we could probably find a quadratic relationship because these points seem to be in the shape of a parabola, but this would not be a linear relationship. So if we found our linear correlation coefficient, it would be very close to 0. The requirements for looking at linear correlations are that we have to have a sample of paired data, has to be a simple random sample, it has to be quantitative data, and we want to look at the scatter plot and confirm that the points approximate a straight line pattern. If there are outliers, they have to be removed, especially if they're known to be errors. If there are some other types of outliers, we should consider whether to include them or not. One thing we can do is to calculate the R value with and without the outliers. Here's the formula for calculating R by hand. This is why we're not going to use this formula, but we're going to use technology instead. So we're going to use computer software or our calculators to find the R value. And also what we can do is once we find R, we can find a p-value to go with it. If that p-value is less than or equal to our significance level, then we can conclude that there's a linear correlation. Otherwise, we can't support the conclusion of a linear correlation. And again, here we're only talking about linear correlations. There may be some other relationship that's not linear. So these are some properties of our linear correlation coefficient. First of all, it has to be between -1 and 1. And the closer it is to either of these endpoints, then the closer our scatter plot is going to look like a straight line. If R is close to 0, then our data is not going to look like a straight line pattern. We can scale the values of either variable without changing the value of R, and it also is not affected by our choice of X and Y. So we can choose either variable for X, either variable for Y. And again, the R just measures the strength of the linear relationship between the two variables. It is very sensitive to outliers. That's why we said that we should consider whether to include outliers or not. So again, if our p-value is less than or equal to the significance level, then we can conclude that there is a linear correlation. Otherwise, there's not enough evidence to support there being a linear correlation. Here's an example. We have some paired data from different years, comparing the cost of a slice of pizza and the cost of subway fare. So we're going to look at those two variables and see if there's a linear correlation between the two. Now we're going to look at StatCrunch to see how we could do this using StatCrunch. Here's our data. I just typed in the year, the pizza cost, and the subway fare. And we're not even going to use the year values. It was an extra thing that I put in here. So if we want to look at our correlation coefficient, what we're actually doing is linear regression. So we do stat, regression, and simple linear. And then we're going to select the column to use for our x variable and the column to use for our y variable. In this one, we're going to use pizza cost for x and subway fare for y. So we select pizza cost there, subway fare there. And here, if we want to predict a y value, in other words, a subway fare for a specific x value, we could do that. We could check this box and put in our specific x value. Now this one I'm going to mark to plot the fitted line so that we can see the scatter plot. So first let's look at our scatter plot. Here's what it looks like. Notice that our pizza cost is along the horizontal axis and subway fare is along the vertical axis. And if we were just looking at the points that are plotted, it looks like it has somewhat of a linear relationship. If we go back to here, it's giving us our correlation coefficient right here. So it's 0.9878. And the p-value, we want to look at this box where it says slope and come over here to where it says the p-value. So our p-value is going to be 0.0002. So we had a test statistic of 12.692 and a p-value of 0.0002. Since our p-value is less than a significance level of 0.05, we're basically doing a hypothesis test here, where the null hypothesis is that there's no relationship between the two variables. We're rejecting the null hypothesis, which says that there is sufficient evidence to claim that there's a linear correlation between the cost of a slice of pizza and the subway fares. And while we're talking about r, we're also going to talk about r squared. This gives us the proportion of the variation in y that's explained by the linear relationship. We already found for the pizza and subway fare costs, we found that the value of r is 0.988. What if we want to know the proportion of the variation in the subway fare that can be explained by the relationship? Then if we look at r and just square it, that gives us r squared equals 0.976. And that means that 97.6% or about 98% of the variation in the cost of subway fares can be explained by the linear relationship between the two variables. In other words, about 2% of the variation in the cost of the subway fares cannot be explained by the linear relationship. Here's some common errors involving correlation. Number one, just because there's a relationship between the two variables does not mean that one causes the other. So correlation does not imply causality. And using averages is not a good idea, because they take out individual variation and they can inflate the correlation coefficient. And again, as we've said before, there might be some relationship between x and y, even if there's not a linear correlation. Now we're going to talk about the regression line. So again, we're actually doing linear regression, and once we know whether there's evidence of a linear relationship, if there is evidence of a linear relationship, then we want to find exactly what that relationship is. And that's our regression line, or our regression equation. And this is going to be just a straight line. Normally we have an equation for a straight line that's y equals mx plus b. In this case, we're using y with a caret, and b0 is going to be our y-intercept, and b1 is going to be the slope of the line. So this is where we can use our linear relationship to predict values for y if we have an x value. And the regression line is just the one that runs the closest to the points in the data set. So we're going to back to our example about the pizza and subway fare costs. And if we go back and look at our results from StatCrunch, actually it already gave us the regression line. It's right here underneath the dependent and independent variables. So where it says subway fare, that was our y, equals, here's our y-intercept, and here's our slope times the pizza cost, which was x. So we could just substitute a y for the subway fare and an x for the pizza cost, and that's our linear regression equation. And also down here it gives you the intercept, the y-intercept, and the slope of the equation. So it really gives it to you in two different places. Notice that StatCrunch also gives you the r squared value right underneath the r value. And here again, when we have it plot the fitted line, we've got our scatter plot, and then it goes ahead and draws the line corresponding to the regression equation in there. So we can see how close our line comes to our data points. Now again, if we have evidence that there is a linear correlation, then we can use our regression equation to make predictions. But if we don't have evidence of a linear correlation, then the best predictor, the best predicted value of variable is its point estimate, in other words, the sample mean. Here's an example. If we have a set of paired data that gives us an R value of 0.942 and a P value of 0.1325, we use StatCrunch to come up with a regression equation, and we get y hat equals 3x. We have y bar, which is the sample mean for the y values, is equal to 12.75. The question is, what is the best predicted value of y if x equals 2.5? So we have to think about this. If we're using, say, a significance level of 0.05, then we would compare that to our p-value. 0.1325 is greater than 0.05, so that would say that there's not enough evidence to show that there's a linear correlation. That means that the best predicted value of y for any x value is just the sample mean for y. So our answer for this would be C, the 12.75.